And I start recording again. Okay. And now let me share with you the whiteboard. Okay. Now, you may ask yourself, what is this deformation quantization is about, and what does it do except for quantum fields? And that is exactly the question that I asked myself around 2010, and it was a huge part of my doctoral thesis. And basically, what I asked myself is, okay, let me take a very simple quantum mechanical system, which is let's say a three-dimensional free particle, okay? And H and P, are just self-adjoint operators, on a dense domain, which I take as the Schwarz space, which is, dense domain in H. Now, what happens if I deform this operator? Okay, just take this operator and deform it. I just want to know what happens to that. The point is, okay, so the deformation formula is dx dy. Now forget the cutoffs. The cutoffs are there to make this thing, a little bit well defined, since we're working with oscillatory integrals. And e to the minus ixy alpha of theta x, which I will write, okay, of h and u of y, okay, on some psi, because these are all operators, and these are oscillatory integrals on operators, so you have to take care of the domain and so on. But I will skip that part. If I will put some references in if you want to see, functional analysis done there. Now, the point is alpha theta of x of h, as I said, is just basically u of theta x, h, u of theta x, where u of theta x is some unitary operator with, the vector u theta x times, let's say, p. So p is a self-adjoint operator in h. I can exponentiate that guy, and then I can take that joint action. The point is that since p commutes, so pi and pj commute. So as I said, the point is that the momentum that vanished, so I could not use that because then the deformed one was the same. So what I can do, what I have given is the canonical commutation relations, which are I h bar delta ij, for I and j being equal to 1 to n. And okay, well, here actually I'm going just from 1 to 3, okay? So I define a unitary operator, so u of p, let's call it, as e to the ipx, right? Where x is this coordinate operator. And then I plug it in and I calculate what the deformation does, okay? So basically I have dx, dy, e to the minus xy, alpha theta x of h, and u of y. Okay, and basically what happened then is, so okay, you calculate a lot. Well, basically, we can calculate what that is. Alpha theta x of h. This is e to the I, well, let me make it maybe of p, px, p squared divided by I to the minus pi x, and that you can just split, and then you take the commutation relations, so you get p plus I, p, commutator of x with p gives you I h bar, okay? And then the third one already vanishes, and that's all there is to it. So this is p plus, minus p h bar squared, okay? The point is, at the end of the day, so you plug this in, then my h theta was basically p minus some constant matrix theta I. No, sorry. This. So H theta was then pi p divided by 1 over 2m minus theta, let me write it with theta ij, xj, and the whole thing squared. Okay, so basically what happened is I went from having an undeformed one, which was just p squared divided by 2m, sorry, to a minimal shift in the momentum. Now, by choosing theta to be in a certain way, so to be a certain deformation parameter, and that I connected to physics, I could prove that this deformed Hamiltonian is basically the Hamiltonian of a particle moving in the presence of a magnetic field. So I could relate those, you know, very abstract deformations to something that is not that abstract. And actually, this is very well known as the minimal substitution. And I did that for a lot of other models. And basically, you can reformulate all of quantum mechanics that is coupled to electromagnetism as quantum mechanics deformed quantized. Okay. And now in the last six minutes, I want to tell you a little bit about my quantum gravity model. So in a sense, one of, you know, the biggest problems that physicists face today is that we are searching for a theory, a complete theory that that incorporates quantum mechanics and gravity with each other. Okay, and there are a lot, as I told you in the first Ringvorlesung, of them, and they are each one has its advantages and disadvantages. And since we are here on a new ground, I thought to myself, let me, you know, do my own way. And I gave myself 3 axioms. First of all, I want the metric, which is sort of the essential, you know, subject in gravity and so on, to be operator valued. Second, I want the flat metric, which we called it, so the Minkowski metric, which is basically, you know, as well, so just the diagonal. So it's a 4 cross 4 matrix with the diagonal elements being equal to -1, 1, 1, 1, and everything else being equal to 0. And third of all, I want this model to emerge out of some deformation quantization procedure. So that is what is called emergent gravity. Okay, so these are the 3 axioms that I put myself. And then I took the simplest commutative algebra that I can think of. So it's an algebra that is generated by x mu. Okay, let's say we have 4. So the 0, 1 is for the time, and 1, 2, 3 are for the spatial components. And I took an algebra that fulfills the following. This is equal to 0. Okay. Sorry. X mu equal to 0. And so I call this algebra the commutative algebra. And now I use the differential, or the Karoubi operator, the differential operator that we define for the universal differential algebra. And so I have a d and I apply it, and I use the Leibniz rule. Now applying d on this gives me dx mu x nu plus x mu dx nu. Okay, this has to be 0 as well, since the d of 0 is equal to 0. Now, one solution of that is that dx mu and x nu is equal to 0, or another solution, which the one more interesting one, is it is equal to c mu nu rho dx rho, where c mu nu rho is, are some, matrices for fixed rho, that are symmetric in mu and nu. The symmetry comes from here because you have here C mu nu rho, and here, you know, you have you have here C nu mu rho dx rho, and you want this to vanish. Thus, mu and nu has to be, sorry, the minus was already put here. Thus, mu and nu has to be symmetric. So if that is symmetric, this vanishes, and you're finished. Okay. Further on, I have now this new differential algebra, right? Which is C mu rho lambda dx lambda. What I also, I thought to myself, I wanted actually, you know, I wanted to have it very easily. So I just take this to be a mu delta rho lambda. Okay. Oh, sorry. Oh, no, that's not correct. I take it to be I delta mu rho a lambda dx lambda, where a is just some random constant and delta is the Kronecker delta. Why can I do that? Because delta mu rho is symmetric in mu and rho, right? Okay, and basically, okay, then I go to represent. So then I represent these operators. I won't not go through this with you, but just let's say we have a representation, which means this abstract algebra is now given, you know, as operators on a Hilbert space. And now I thought to myself, okay, then I start with the with a flat metric, because, you know, in loop quantum gravity, for example, they cannot reconstruct the flat metric. So I said to myself, let me start with that. And we define this line element as eta mu nu dx nu, where I take here the sum over mu and nu. And now I deformed this metric by using, you know, this formula that I had before. So dx dy e to the minus xy alpha theta x of eta, okay, and alpha y of, no, sorry, and u of y. I use this Ringvorlesung deformation to deform this metric, and the unitary operators were generated by these x's. Okay. So I take unitary operators generated by these x's and I plug them into this formula. And what basically happened is that the flat Minkowski metric turned into a conformally flat one. And the conformal factor is minus 2 a mu theta x mu eta. Okay. Now, by choosing a and theta to be in a certain way, I obtained a deformed Friedman-Robertson-Walker model. And further on, you can choose the constants in a way such that you get the old FRW model. Basically, all I did was to choose a theta 0I to be the Hubble parameter. So you see, we started with a very abstract concept of a non-commutative or of a commutative algebra, but to that I knew how to construct a differential algebra. This allowed me to construct a flat metric. Now I deformed this flat metric by using the formalism of Ringvorlesung and so on. And by deforming this, I obtained a curved metric from a flat metric. And, you know, there's a little bit more that goes into that, but that is sort of the gist of what this quantum gravity model can do. And it is, in a sense, a fusion of those two ideas. That's all that I wanted to tell you, basically. I mean, there's a lot of interesting stuff, but I mean, for that, the time has run out. So, so are there any questions so far?
Yes, I have a few questions.
Sorry, just let me make you louder. Yes?
Thanks. So the first one is, how can we talk about equations of motions or moduli space, so to say, in the language of non-commutative geometry?
I can refer you to some literature. It is a little bit more complicated there, as far as I know.
But is there any correspondence to this concept in non-commutative geometry?
Yes, yes. To any, basically, I mean, if I can say it that way, to any concept of commutative geometry, there is a non-commutative concept corresponding to that. where you have, you know, connections and Riemann curvature and all that.
Okay.
Right. What was your second question? You said you had a second question.
Oh, the second one is, can we introduce supersymmetry to non-commutative geometry?
You are currently the only person in this conference.
Sorry, can we introduce a symmetry into non-commutative geometry?
Supersymmetry.
These are the good questions. Yes, you can. There is work done by Klaus Siebold in that direction. You can introduce supersymmetry into non-commutative geometry, and by Julius Wess, actually. So Julius Wess was, you know, also one of the founders of supersymmetry, and he was very interested in non-commutative geometry, and you can put those two concepts together and you can, you know, do a lot of calculations in that direction. But the point is, for example, they work with matrix, you can do that. Yes, you can definitely.
Okay.
But the point is, I don't know how, you know, what the current level of progress on that is. But yes, you can definitely do that.
Or maybe can you give me the reference in the chat?
Yes. Maybe I can send you an email, Sean.
Okay. Yeah.
I can look up some references and also ask Klaus Siebold, which is you know, an emeritus professor here at the University of Leipzig, and he did some rigorous work in supersymmetry alone, and then also in non-commutative quantity theory and supersymmetry as well. But yeah, okay. For those of you who are maybe not that familiar with supersymmetry, so you have your, you know, your theories. In physics or in quantum field theory, we have bosonic theories and fermionic theories. Bosonic theories usually correspond to particles with spin that is an integer, and fermions with spin that is half integer. Okay, and the point is that in certain theories they come together, but in general they are, you know, separated from each other. Now, the nice thing about supersymmetry is that they found, you can see it already in very easy examples. For example, if you look at the, you look at the harmonic oscillator for bosonic particles, and there the Hamiltonian is basically given by A cross A plus 1/2. And if you do, you know, the energy, so you calculate the energy, eigenvalues of that, and so on, you see that you have this zero infinite energy, right? And for fermions, the interesting thing, it comes with a minus 1/2, okay? So this is the bosonic and this is the fermionic. And, you know, because at the end of the day, what you want to do is calculate the eigenvalues, and then you sum over all eigenvalues from n equal to 0 to infinity, right? So, and, you know, the sum over 1/2 for n equal to 0 to infinity is just infinity. So this is the 0 point energy, vacuum point energy, or vacuum energy also called. And the nice thing about supersymmetry is if you just randomly add those two together, this 1/2 cancels. And so for every boson, there is a corresponding supersymmetric particle, which is, you know, the supersymmetric particle, which is the fermion. And you can do them in such, you can, you know, formulate theories in such a way that they become renormalizable. That is what I was talking about earlier, that there's this question of renormalization. And so renormalizing these theories, and because in the end you calculate S matrices, which are scattering matrices, and they're extremely complicated, and you have to, you know, do a sum expansion, and the conversion is always an issue there. But in supersymmetry, in the sense, there are, you know, simple models that can take care of that, and thus this is a great hope that one can find it experimentally, and that theoretically it gives us certain assistance. And putting on that non-commutative, so non-commutative quantum field theories can help you with renormalization if you do it in a good way, but in general they don't, right? They're very complicated, and they add additional difficulties to the theory. So putting that on top of supersymmetry usually is a what do you call it? It's a very brave thing to do, and I don't think that it in general gives you good results. So that was maybe the question. Sorry. Are there any other questions? Maybe general picture questions, you know, of what we were doing during this. Well, I mean, the point is, you know, with the corona and so on, we were all a little bit confined to our homes and office spaces. But, you know, as soon as this is a bit, you know, more chill, which I don't see it be very soon, we can, you know, you can come to my office and we can discuss some questions if you have anything or so. Or if you find anything interesting and you would like to work on it and you think, you know, my assistance can be of any help, I would be glad to participate with that. Well, and so if all of that is clear and enough was said, then I thank you all for your attention, and I hope you were able to take something with you. And thank you, and see you. Bye.